Hello, today I will talk you about the outcomes of a Marie Curie European project called AMADAM, Advanced Design Rules for Optimal Dynamic Properties of Additive Manufactured Products. In particular, I will talk you about the fracture mechanics of additive manufactured crack-like notches by digital image correlation. I am Gian Giacomo Minac from the University of Bologna. The AMADAM project is a Marie Curie project that involved several countries: Italy, Croatia, Serbia, and Bosnia-Herzegovina, and some academic partners, the University of Bologna, and the faculty of the Kraljevo of the University of Kragujevac in Serbia, and some industrial partners, Unodesign in Italy, Topomatica in Croatia, and Flamingo in Bosnia-Herzegovina. The aim of this project is to determine design rules for additively manufactured products, in particular as regards the dynamic properties. So, in the framework of the projects, design criteria for fatigue were found, as in particular as regards the properties of metals and the specimen size and shapes to get to these properties and their post-processing. And also we dealt with the fracture mechanics properties, in particular with regarding one specific point: how to induce cracks in additively manufactured products in any desired position and direction. So we will talk about crack-like notches. So they are notches that we can produce by additive manufacturing in any point and any direction. But are they actual cracks? Is it possible to make them more cracks than crack-like? And how will we check the results of our experiments? We will use digital image correlation on specimens that are specific for this application, and that allow us to test the different mixed modes for fracture mechanics from mode 1 to mode 2, with all the mode mixities in between. And we did it for metal and plastics. So, talking about crack-like notches, here we have a picture of them. So, by additive manufacturing, it's possible to produce crack-like notches in any direction, any position, but not real cracks. In the picture on the left, you see the crack-like notch produced by additive manufacturing. On the right is how a real crack is produced. So you make a notch, and then you pre-crack by fatigue loading and obtain something that is very visible in the image. For our technology, the minimum radius of curvature is around some tenth of micrometers, depends on the technology. So Is it possible to pre-crack these notches? Could be, but not. It is not general because it depends on the direction and position of the notch. So, in very trivial cases, it would be possible, but in those cases, the notch could be done even by normal technologies, what it is available up to now. And moreover, when you do pre-cracking, you know the direction where the cracks will go. While in this case, it's not possible if the geometry is complicated. So maybe you have a crack line notch in one direction, and when you start pre-cracking, the crack goes with a slope in a totally different direction. That is out of our scope. We did some previous research before starting with the project, of course. This gave us the idea. And of course, we started with something that is more common than the specimen we actually used in this project, that are the CT specimen, compact tension. And so the crack is here at the end of the notch in between the two holes. You see also the dotted part pattern that we use for digital image correlation on the specimen. We test the difference between manual induction of the crack by means of a razor blade and by digital and by additive manufacturing. Here in the graph, you see the difference between the different built-in direction of the specimen. So it can be seen that when you induce the crack by the additive manufacturing process, so SLS here, there's a strong anisotropy as a function of where you put the crack. So if the crack is orthogonal to the build direction, the properties are the lowest. This paper shows all the details of the work. Here you can see the specimens that we used. We made a previous work on this specimen, starting with plastics and also with other additive manufactured items. With these specimens, you see here the alpha disc. A variety of mixed modes is attainable as a function of where you put the rollers under the disc. So you have some degrees of freedom. You have the distance S1, distance S2, and the slope of the crack alpha, and somewhat also the length of the crack, but that's not really important. It depends on the ratio between the length of the crack and the radius of the disc. So K1 and K2 are a function of the load, of the dimensions of the crack, and of two shape parameters, epsilon1 and epsilon2, that are calculated by finite element. More details are shown here in this paper of 2013. As said, we use the digital image correlation for detecting the displacement and the strains and the stresses of the specimen. Here you can see in the picture the whole experimental setup. You see it's very easy. It's just a camera and a PC with a specific software to elaborate the images, and some device to apply the loads in a controlled way. So we can measure all the displacement field, and it's a full field technique. You can get 2D data or 3D data depending on if you are using one or two cameras. There are advantages in using two cameras, but also some complication of the setup in particular as regards the calibration. The correlation is performed by some speckle pattern, and the key point is the randomness of the pattern, so that the computer can identify some points characterized by a specific partner and see where these points are going after deformation. So the computer can find the point by point the displacement, and then by derivation you can get the strain. Sometimes all these data are automatically fitted by the computer to get some smoothed plots. To get these experimental results, we employed two different machines from EOS, one for metal and one for plastics. Both use the same principle. So the laser melting of powder that is deposited layer by layer. So we used Maraging steel to test metals, and polyamide for plastics. You can find the data sheets here in this slide, and in the picture are shown the machines that are available in the 3D Impulse lab in Craiova. So the measurement setup that we choose was the 2D, because we don't have large displacements. We have a very small area of interest at the crack tip. So, but it's possible that we want to change the zoom, and it would be complicated to do it by 3D measurements because you need recalibration every time, while in 2D it's much more straightforward. The only point is you have to guarantee that the specimen and the camera are always parallel, and so we did it by a suitable experimental setup. We used a free software to make the correlation that is produced by GOM, and it's possible to download it directly from their website. With these parameters, we tested these configurations with different values of S1, S2, and the angle alpha to get different fracture modes, 1, 2, or mixed. And here you can see mode mixity. 3 specimens for each configuration. And we did also some indentation test when the calculation of energy was needed in order to take out the energy due to indentation on the loading point. So the modeling part was different for the two materials because while the Maraging steel can be considered linear elastic, so with a very limited plasticity on the crack tip, the plastic cannot be considered linear elastic at all. So we modeled the Maraging steel using interpolation of the results of the experimental results by means of the formulation of Williams, and here is the formulation, and the stress intensity factors are found from this formulation. You can have a full description of the method in this recent paper. These are the results for the displacement in the case of Maraging steel for all the configurations that we tested. Here is digital image correlation. Here is the theory, and the third is the deviation from the theory of the results. You see that the deviation are generally low, with some cases in which they appear to be larger. These are the results for displacements. Okay. And here in the table, the value of K1 and K2 that are computed by the standards. So that by taking into account just the failure load. And here it's by digital image correlation with a column of differences. Here we have also the two type of cracks. The first SM are cracks obtained by pre-cracking, not by additive manufacturing, and these are all by additive manufacturing in several cases. Of course, here we did it only in pure mode 1, because it's the only thing you can do with pre-cracking. So this is a point of our investigation, and we cannot do differently. While with additive manufacturing, it is possible. So here we have a deviation from theory, and you see that there are quite some. So what does it mean? So here it's easier to see that this digital image correlation method are the red ones, and the classical methods are the black ones, as a function of mode mixity. So we have the stress intensity factor as a function of mode mixity. And so we have a very large discrepancy here in mode 1, because why is this? One could think, oh, that's probably there's the plasticity of the crack tip. That is not the point, because if you make some simple math, you find that this could be could account for 5% of this difference. The point is that K1 depends on a three-dimensional state of stress at the crack tip, while the digital image correlation considers only what happens to in the surface, and the surface is in plane stress conditions, while in general the rest of the specimen is not. And what happens when we change mode mixity up to mode 2? This effect disappears, because in the mode 2 this effect is not important anymore. This as regards the use of digital image correlation in these conditions. What we see about the use of additive manufactured cracks with respect to pre-cracking, we see that there's a 25% higher stress intensity factor. This is okay, like we consider the notch a crack. Okay, so we can just apply this correction factor to our results in general. We hope it is possible to apply to all the cases. For polyamide, we used a different model based on the J integral that is possible to use when you have a larger plastic part. So we used two methods. One, calculate J integral from the load displacement curve by finite element method, and the second directly from digital image correlation. So here you have how it is calculated the J integral. You need the energy, and the energy should be computed without the indentation part. So we made test and we took out the indentation from the energy. And here you have the expression of the J integral. I will not go into details to calculate it from the both finite element method and digital image correlation. To get the energy, we use the well-known Ramberg-Osgood constitutive equation. Of course, this is a point of investigation to get improved results, but we found out that also with this simple assumption, we got good results that are summarized in this paper published this year. So these are the results for polyamide. We have the displacements and the strain with in both direction, x and epsilon. And from these displacement fields and the strain fields, we get the J integral calculated in several paths. The J integral should be a path-independent quantity, but of course this is ideal when you do it in a discrete way. If you change the path, you get slightly different results. So here we have the mean J integral calculated over several paths for the standard method and digital image correlation method. And you see that the results are, let's say, acceptable. Here in the graph, it's easier to appreciate that there are much less differences in the J in this case than in the stress intensity factor in the previous case. So also you can see that the difference between J integral between the two cases with the pre-cracking specimen and the additive manufactured specimens in mode 1, it's not so high. So in this case, it's easier to employ this method to make cracks in additive manufactured components. And it is quite nice to see that the calculation of J integral by DAC, it's a very precise method, and the point is that can be used in real components. You don't need to have specimens, so you can just paint the external part of a component, load it, provided that there is a crack, of course, and get results locally. So, as I told you, the J integral of the notch induced by additive manufactured method is just 12% higher respect to the one obtained by standard methods, but this is within the experimental error. So we don't know actually there is any difference. And we see also that there is, in general, for both methods, a minimum in the J integral function. So the whole situation is not pure mode 1. It's okay. The mode 1 should be dominant, but with a component of mode 2 you need less energy to break the specimen. That is quite interesting. Concluding, we have shown two digital image correlation based techniques to find out the fracture mechanics relevant properties of two different materials obtained by additive manufacturing with embedded additively manufactured crack-like notches. And what we found out is that it is possible to evaluate the stress intensity factors using the interpolation of the model of Williams. And it is possible to evaluate the J integral by digital image correlation with good approximation with respect to the standard methods. And we found out that the results obtained by the first methods are overestimated in case of pure mode 1, while tend to be similar to the standard methods when you go to the mode 2, while for the J integral calculation, the results are perfectly in agreement with standard methods. I thank you for the attention, and here in the slide you have the partners and the coordinator of this project that is coming to its conclusion now, and it provided very useful results in the field of the design rules for additive manufactured components under dynamic loadings. Thank you for the attention.